Hello, everyone. I'm excited to present Emendo technology, making any gene targetable to you today. Yeah, that's a disclaimer slide. So let's just review quickly the bottlenecks as we understand them, still holding the editing field back. First, of course, safety always still remain a concern for the field. Genome accessibility is still limited, even with the quite ubiquitous PAM of the NGG nucleases. Delivery, always a challenge. IP remains a challenge in the field, and of course, immunogenicity. So at Emendo, we have established a platform which is consisted of 3 different platforms: a discovery platform, a computational, and an engineering platform that work synergistically to address each and every one of the limitations I've mentioned. From these platforms working together, we have generated a panel of nucleases that are very diverse in properties, and we can choose the right nuclease for each application. And from that, we derived therapeutic compositions that are highly optimized per target sequence, and they are optimized in the context of a specific delivery modality. So the discovery platform was set to find novel nucleases with diverse properties. So for example, PAM diversity. Cumulatively, our nucleases can now cover 86% of the human genome, in comparison to the widely used NGG PAM that can only address 5% of the human genome. In terms of size diversity, we can use any delivery modality our nucleases are compatible with, and in addition, our nucleases are discovered from sources that humans were never exposed to, eliminating any issues with pre-immunity to the nucleases. The engineering and optimization platform is designed to increase specificity and systematically eliminate off-target and the subsequent translocations. Even in the most stubborn and vicious ones, we are able to increase specificity to the extent that we can do allele-specific editing, and being able to selectively edit one allele, leaving the other one completely intact, based on a single base mismatch between the alleles placed anywhere along the guide. This enables our own pipeline of indications, which is highly differentiated as in focused on dominant indications. We have also used the engineering platform to increase activity of nucleases very significantly, 3- to 4-fold genome-wide very robustly, without losing specificity. So we were able to break this activity specificity trade-off that you could usually see when you optimize nucleases. We also engineer the guides to be more manufacturable, to shorten them, so a lot of flexibility around all the moving parts of the nucleases. And we're also developed a very extensive computational platform. We are harnessing machine learning and AI tools to be able to now predict PAMs and tracer, to make the engineering more efficient, to make the libraries smaller and the screening process faster and more efficient. We're also doing cryo-EM to have the 3D structures of the nucleases and to have structures, sequence structure function in place for these nucleases, now also accumulating all this enormous amount of data into centralized database where we can keep building the machine learning tools on. So the discovery pipeline, we have discovered over 10,000 nucleases in silico. 300 of them were validated to be active in vitro. 120 are active in mammalian cells. This requires to determine the right PAM and tracer to have activity in vitro, but then activity in mammalian cells is the next bar. 12 were fully characterized and 2 extensively engineered. And as I said, the nucleases, you can see here the frequency of the PAM within the coding genome, and each nuclease has a bit of a different representation within the coding genome, but cumulatively, we can address 85% of the human genome. I want to show you one example, or actually 2, on the power of engineering and what we can do with this. So engineering is really the heart of the company, and this is what enables Emendo to achieve the editing objectives. And in this specific examples, you can see a nuclease that we started with a wild-type form that is not allele specific and is not even very active. So in this example, first consider that the y-axis is the unedited allele, so the non-treated, these are 2 healthy, intact alleles. Each one of them represents 50% of the genomic loci, so in terms of editing, 50% is really the 100%. And you can see that there's really no allele preference and not very high activity in general. But after engineering these nucleases, you can see the bar on the right side where we have been able to achieve almost complete allele specificity, being able to really knock out almost completely one allele and leave the other one completely intact, and we can do that both ways. So if we can edit each of these alleles as required. And I think anyone who knows editing can appreciate this achievement. In terms of off-target and safety, in this example, we're using OmniA1. This is one of our earlier discovered nucleases, and this is actually a head-to-head comparison with SPCas9. So on the most left bar is the on-target site. As you can see, OmniA1 in pink cleaves almost 100% on the on-target site. But the rest are off-target sites, and for SPCas9 in gray, you can see 14 off-target cleavage sites, while for OmniA1, there's only 2. Still, these 2 were not acceptable at Emendo for a therapeutic composition, and we have taken these nucleases to engineering, and I don't have a laser here, right? But you can see on the graph that the OmniA1 variant, we were able to eliminate the off-target altogether and generate a perfectly specific therapeutic composition. On the middle panel, that's a different assay that we're using to validate the off-target cleavage. The most bottom one is the SPCas9, and as you can see here, it's very visual how noisy the nuclease is. And the middle panel is the OmniA1 in the wild-type form. It is already much better and much more specific, but still some off-target sites. And in the upper panel, it's the engineered variant, perfectly specific with a single cut site on the on-target site. On the right side, that's a different assay testing for translocations, so off-target mediated translocations. And here we compared the OmniA1 wild type with the engineered variant. And while the wild type has still some translocations, the engineered variant has absolutely 0. So for delivery purposes, we use different modalities of delivery depending on the application. We are packaging our nuclease in an mRNA format with 2 guides in LNPs. This is in vivo data, and this is actually excision. So it means that we're packaging the mRNA of the nuclease plus 2 guides in a single LNP particle for an excision strategy where we see around 30% excision efficiency, which is actually quite high for in vivo, and this is quite early data, so there's a lot of a place for further optimization. We're also developing additional delivery system in-house, which is based on lentivirus like particles, which we engineered to pack RNPs. So it's of course not integrating, it's not even DNA, it's actually packaging RNPs, and so it's a very transient expression of the editing machinery, and we get really very nice efficiencies of editing in vitro at this stage, taking the system further to in vivo use. Just a few words on IP, as I touched upon in the beginning. There was a lot of attention on IP around nucleases, but I would like to highlight a different IP issue that we have identified early on in our editing work, that guides are actually heavily patented. And if you look at different target genes, sometimes the guides are so heavily patented that you can't find any guides available. So we've established in-house, we've developed a software to be able to screen guides against the patent literature. We have purchased a database of all the sequences from patents. It's a huge, huge database. It's terabytes and terabytes of sequence data from all different patents, figures, sequence listing, all that. And whenever we start working on a project, we take the guides and we screen them against the patent literature to find, to actually screen out guides that are found in patents and to continue with clean guides to composition development. And interestingly, if you look, these are few targets from the immuno-oncology space, like TRAC, like B2M, like PD-1. So if you screen out all the NGG guides, you are left with zero, no guides to work with. And so this is where non-NGG nucleases come in very handy, and once identifying this issue, we've started developing the compositions for these type of targets using a non-NGG nuclease that makes other guides available that are clean from patents. So now moving to our own internal programs, and the first one and the most advanced one being severe congenital neutropenia. This is an immunodeficiency disease, and it's a dominant negative indication. So to address that type of indication, you would need to do allele specific editing. In terms of mechanism, it's neutrophil differentiation defect, meaning that when neutrophils, as you see in the upper part, when neutrophils differentiate, HSCs differentiate into neutrophils in healthy people, in SCN patients, this differentiation gets stuck in the promyeloid stage, and the cells just go to apoptosis and die. So these children are born with very low neutrophil count, sometimes close to zero, and they are exposed to recurrent life-threatening infections. And until about a decade ago, they would not survive the age of 10. This is when G-CSF was approved as treatment for these children, and they get daily injections of G-CSF, allowing them to reach adulthood, but exposing them to severe risk of developing MDS and AML. So there's definitely a need for a curative solution, and we have developed here a very novel editing strategy. We, first of all, we knock out specifically only the mutated allele, leaving the other one completely intact, since this protein, the neutrophil elastase, is essential for neutrophil functionality. So we had to preserve the healthy allele. So we were able to show that allele-specific editing, in this case, knocking out only the mutant allele, was able to restore the healthy differentiation and function of neutrophils. The neutrophil levels normalizes, as well as the monocytes level normalizes. This program is done in an ex vivo autologous editing approach of HSCs, and it is done in collaboration with Seattle Children's Hospital, with University of Washington and the Severe Congenital Neutropenia Registry, and also with Tübingen University Hospital in Germany. We have had a very successful pre-IND meeting with the FDA earlier this year. I have to note that they really appreciated the off-target profile and the safety profile we presented to them. Moving to IND later this year and first in men early 24. A second program I'd like to tell you about is familial hypercholesterolemia. This is an in vivo program targeting the liver. It is, we are also here taking a very novel editing approach. We do not target the PCSK9, rather we are directly upregulating the LDLR gene. And this approach has been proved to be very efficient, as I will show in a minute. We are packaging the OmniA2, which is a very short nuclease with 2 guides in an LNP, and without correction, we are able to upregulate the expression of LDLR very significantly. So this is a very physiological approach, so we are actually addressing the mutated disease-causing gene. It is universal in the sense that it is not mutation-dependent. It is very potent. We show a very robust increase in the LDLR expression. So just briefly, around 40–50% excision on the genomic level can lead to 2.5-fold increase in the mRNA of LDLR, and we see 3-fold increase in the expression of the protein on the surface of the cells, and 4-fold increase in LDL uptake for when we compare it to non-treated cells, and 2-fold increase when we compare it to standard of care, which is not standard, but PCSK9 knockout plus statins together. So it's still 2 times more efficient than combining these 2 treatments together. In terms of our pipeline, we have programs in ophthalmology, hematology, and additional liver programs coming up. And yeah, thank you. Thank you for listening today, and the Emendo team for generating all the science and hard work. Thank you very much.